and the private key. So the private key, like it would sound like, you keep it secret. You don't tell anyone this number. And the private key is basically just the factorization of n. So you have p and q. You keep them close to your heart, and you don't let anyone know.
Oh, close to your heart.
But then there's also the public. So basically, you want people to be able to send you encrypted messages. So you're going to publish these numbers out into the world. The numbers are n and z. And we're assuming that it's really hard to factor n because these numbers are so big. So even if you were just counting 1, 2, 3, 4, and so on, all the way up to q and trying to divide into n, it would be maybe computationally difficult. Like these are just 20 bits, but most people use like much more, like maybe 256 bits or something. Or even more, depending on how much security they need. And so we're just going to assume that n is really hard to factor. So nobody can find out what these p and q are. And what these two numbers, the n and z, allow someone to perform this encryption operation. So we're going to go find out what that is. Yeah, so basically, you take your message, which is just a single bit, either 0 or 1, and then you can find a random number in from 1 to n minus 1. And so that's not difficult to do, you just find a random number. And you square it, so you know it's going to be a quadratic residue. And then you multiply it by z to the power of n. So remember, m is 0 or 1. So if m is 0, then you have just x squared, which is some random quadratic residue mod n. If m is equal to 1, you have a quadratic non-residue with Jacobi symbol 1 multiplied by a quadratic residue, which of course has Jacobi symbol 1. So the result is something with Jacobi symbol 1, but it is still a quadratic non-residue. So you can't find the square root of it. And then, so you just send this value c to whoever it is that you're trying to communicate with. And on their end, they can perform the decryption operation. So because they know the values for p and q, they can just calculate simply the Jacobi symbol that we had before, the x to the p minus 1 over 2, and determine whether or not the number is a quadratic residue or not, because the two Jacobi symbols for mod p and mod q will be -1 if it's not, and +1 if it is. And that is basically the whole idea. So we can check it out. So let's try to encrypt something, I guess, with these numbers. So first you give it the value z, and then you give it the value n. So this is the public key of the person you're sending the message to. And then, should I encrypt a 0 or a 1? What do you think?
0.
0? Okay. So this is our message C. We can't really tell whether it is a quadratic residue or not. We can calculate the Jacobi symbol. There's an efficient way to do that, but it's not going to tell you whether it's a quadratic residue or not, because there's still a 50% chance whether it's one of the quadratic non-residues with Jacobi symbol 1 or the quadratic residues with Jacobi symbol 1. And then if we want to try to decrypt it, so we first have to input our P and Q from up here. That's our secret key. And then we give it the value of the message. And it should tell us, yeah, 0. So that's what we had before. It basically just computed whether or not it's a quadratic residue modulo P and Q, And since it was, it gave us the value 0. And then last thing is, why is this even relevant? Well, one of the cool things about it is it's, well, yeah, like we said, it's the first probabilistic public key encryption scheme. There's still a lot of ways that it can be improved upon to make it much faster, less heavy, like use less memory to send the messages. But what's really cool about it is also that it's got some homomorphic properties. So what that means is that even after you encrypt it, and it's still in the encrypted state, you can perform some operations on it that will change the original input in a predictable way. So basically what it is if you
like if I multiply input by 2, would my output multiply by 2?
it's not exactly like that. Basically how you can do it is, since we're only dealing with bits, you can do the bitwise addition called XOR function. And if you just multiply the two encrypted messages, that is the same as computing a bitwise XOR. And so that sort of thing is useful because if, say, you have encrypted health records and you want to perform like some sort of predictive analysis on them, you don't want to reveal everyone's health data. So you encrypt it, and then you can perform the same operations that you would normally do, and then send the information back, where it can then be decrypted, and everyone is like safe and private, and you still got to do your cool math. Or maybe something else, just like cloud computing itself. Like you send it off to some other place where they do the calculations and they send it back, but you don't want them to keep on amassing amounts of your data. So you use some sort of encryption and they can still perform the same operation.
Oh, that's cool.
And that's about it.
Yay! That was awesome and mind-blowing. I didn't get half of it, but it was cool.
Any more questions or anything?
Why did you choose this topic?
I don't know.
Good question.
I've just like done some research on cryptography. I like this one because it's got a bunch of cool number theory stuff and like abstract algebra, but then in the end you actually get to apply it. Like you were saying, like Chinese remainder theorem, when do you get to see that in action? Today you get to see it. Yeah, I mean, I can do other ones, maybe some of the more practical ones. Like if you click on like your browser or something, there's like a lock. You can click on it and it's gonna say what type of encryption they're using. So they might use elliptic curve or RSA or AES, and I can give talks on them if you want.
Yay, and our next series on our YouTube channel, so sign up guys.